Well, I think you'll find this exciting. This is using differential equations in problem solving, and I hope you've got your skills up here. Have a look around the screen. There are some practical problems here. It's getting exciting because you're going to find an important use here for differential equations, and a practical situation where you might be looking at the rate at which the deflection, the bending of that beam, increases out along its length. Possibly got some engineering applications there. And over here we have water kept at 100 degrees Celsius flowing through that pipe. At what rate does the heat go through to the outside and the temperature change on that outside surface, that sort of thing. And here we have a resistance capacitor circuit here. You might know much about physics, but we can still analyse the maths of that circuit. And you'll be doing one of those a bit later on. Well, what about the evaporation of water from a body of water there? At what rate is that V changing, the volume changing? Okay, so we're going to be doing some of these, and don't get frightened by the fact that the answers may not be nice integers. These are practical problems, and you've got to stick with your belief in what you're doing, and when the numbers don't come out perfectly, you say, oh, well, that's life. That's the practical world. All right, we'll come down now and let's have a look at some problems here. And we're going to split this into two. The differential equations, first of all, are going to be those that you can solve by direct integration. And then there's going to be some differential equations that need to be separated, separable ones, and see the applications there as well. Okay, so here's the one we were speaking of. A thin horizontal cantilever. A lever here that is going to go up and down. B can go up and down. Has a deflection of y meters at a distance of x meters from the fixed end. So get your head around that. Make sure the diagram has all that information on it, and I think it does. Now we're going to be given a second derivative here. So the second derivative of y with respect to x. So as we go out here, how y is changing is given by this one. Okay, find the equation for measuring the deflection from the horizontal at any point on the beam. And hint, when x is 0, what are y and dy by dx right back here at 0. When x is 0, right back at the fixed point. So at the fixed point, you might have to think about that. And then determine the greatest deflection of the beam. All right, well, let's go down and see what we can do with it. So first of all, let's try to integrate this. So the deflection of the beam is going to be y, but we've got to get dy by dx first. So let's integrate straight across there. Okay, so first of all, simplifying the expression there into neg 1 on 10, 1 take x squared. Instead of that, put x take 1 squared. Does it make any difference? No, it doesn't. Okay, when you square that out. So we'll get that x take 1 squared in there, makes it easier later on. And then here, let's try to simplify it. So we'll put the constant out the front. And then we're going to integrate this, increase the power by 1, divide by the new power, multiply by the derivative of x, if you like, there. Okay, so we've got plus c on the end. And so simplifying it, we've got -30th. Okay, so I think that's okay, that integration to get the first derivative here. Now, but we are told that x is 0, then dy by dx will be 0. It's a fixed point, there's no deflection there. And also at x equals 0, y would be 0. Let's go back up again and just have a look at that up here. See here, at x equals 0 at this point, there'd be no deflection, y would be 0, and dy by dx would be 0. It hasn't changed at all at that point because it's fixed. So it won't sag or bend there. Okay, so we can sub those values in. Okay, and get c as -30th. Just check the calculation there, subbing it in. Okay, so we've got an expression now for dy by dx, and we can go again. Another integration will bring us back to y, won't it? So therefore, let's keep integrating this, the integral of this, put it out the front, the constant out the front, increased power by 1 divided by new power. And then we've got negative 30 out the front, so that was plus 1, so that becomes x. We took those negative 1/30 out the front. Okay, and now we can actually have another constant added. Notice it's not going to be c. You could have used C1 and C2, but having used C, we're not going to say there's any connection here between this integration and the prior one, so we've got to use a different symbol there. That's important because we're not going to link those functions. If we put C here, it's suggesting that it's the same constant as in the first instance, and that wouldn't be appropriate here. Okay, so now to evaluate D, x is 0, y equals 0 at the end, where it's fixed, substituting those values in, x is 0, y is 0, we get this, and then we can get d is 1/120th. So the deflection equation, coming back through two integrations, is going to be this one here, and the maximum deflection is when this is going to be equal to 1. Now, let's have a look there. The y max, therefore, is subbing that in, sorry about that, subbing x as 1 in, and we get this, it'll be 0.025 metres if you work that out, and you can then change that more practically to centimetres. Okay, so we've got that maximum deflection at B. Okay, so let's have a look back up here at what that would mean. Determine the greatest deflection out at B here. How far is that? That's 2.5 centimetres. So do you get the idea there of what we're doing? We're trying to find that maximum deflection. We've got to do two integrations of our second order differential equation. So we come back twice there. Okay, so let's have a look now at doing some yourself. So 8E1, what we've got here is some rather trivial one here, but go through, there are some interesting ones. So you might not do all of them. I think you should do the ones that are of a more practical nature. These here, this one, and again, a similar one here, a plank of wood. And here, I think the motion problems with sines and coses are important in this course. Differs from other courses where it's just algebraic functions. All right, so pause the presentation there. So I'll just go back up, and you can pause at various places. There's 1, 2, 3, and let's go down 4 and 5, and 6 and 7. And have a go, and I'll show you the answers now. Okay, most important to show all the steps of working there. Let's have a look at question 2, 2 and 3. Funny numbers, you'd expect that in practice. 4, and we get 5, or 4 and most of 5. 5, we'll just try and get B there, not 5A. And we'll get a bit more in. B and C. And D. Going to question 6, A and B. Question 7. All right, how are you going? Getting used to those strange numbers? Let's go down and have a look at doing some involving separable differential equations. Oh, I didn't notice that. Screen clippings here from Hayes and Harris Publications should get their book, but that should be separable, not separate, separable differential equations, not to worry. Okay, so let's have a look at this first problem now, and just bring it up here. fluid's flowing through a thick-walled insulation tube with thermal conductivity of that. Now, you don't need to know what's going on here with the physics of it, but we're going to look at just the maths here. So don't worry if you don't know about thermal conductivity. We'll still be able to go through the problem, I think. Okay, so what's going on here? The inner radius is 0.02 metres, so let's make sure, there it is, that's marked on the diagram. And the outer radius is 0.04. Okay, so it's important to have those two marked on the diagram. Okay, the fluid maintains the temperature on the inner wall of the pipe at 600. Heat is lost through the tube per metre of length according to Fourier's law. You probably haven't done that, but it's a differential equation. Okay. Q is the heat transfer rate per metre length of tube. Okay, R is the radius from the centre of the tube, T is the temperature in degrees Celsius. The heat loss per metre is 680. Now here, watts, but calculate the temperature of the tube. Now here, we have a rate of change. So we need to work that into the problem in a minute. So here we go. Here is our equation, and we want to calculate the external temperature of the tube. Now, how are we going to do that? Let's have a look. What can we do in here? External temperature is T, isn't it? T is the temperature in degrees Celsius. Okay, so T is the temperature in degrees Celsius. We want to know what it is at the external part of it, at the external part of this tube. Okay, so the first thing that we might do is to actually try to solve this differential equation. Okay, and what we're going to do down here, they've done it slightly differently here. First of all, we can put in some constants. Okay, so R is, hang on, get rid of that. So R is the centre of the tube, but here, what can we put in? Do we know any of these things? We know here that K is 0.2, and back up here, hang on, I'll just go back up and have a look at whether we got that. We've got it up here. Okay, so we can put that in, and then what we're going to do is to try to integrate this function and with respect to R, and see if we can solve it. So they've done something a little different here. Okay, separate it like that. Let's perhaps do it slightly differently there, and say, can we do it in a different way? So here, dividing both sides by R, we would have 680 over R equals 2 pi times 0.2 dt by dr. Okay, so here integrating that, that would, well, we could, what they've done is put the 680 over the other side. So we'll do a similar thing here. 1 over R equals 2 pi 0.2 over 680. Oh, sorry, got a negative there. dt by dr. But they've set it out slightly differently here. So I'm going to replace this with what we would normally do. So I'd say the integral of 1 on R dr is this, which is negative 0.001848 times the integral of dt by dr. Okay, so then integrating that, ln mod r is equal to, here integral of that is, I'll put all this in, it's just t plus c. Okay, so they've split, we don't usually do this at this level, they've split the dr away from dt, and we won't do that. We'll put it this way, dividing both sides by r, 1 on r, and then integrate that dt by dr. So this is a preferred setting out over here. So now we can evaluate the constant at r equals 0.02. We know the temperature if the, the heat loss was 680 and the temperature was 600 there. So we can actually sub those values in, and here we've got our T times by this over here, and plus C. So we can rearrange that. Okay, so just notice this is the preferred setting out for that problem, dividing by R and so on. So here we can now put our formula together and say, okay, so ln R is equal to this thing here. Okay, so when R is 0.04, we can actually sub into it. Okay, so we've isolated T, that temperature, and we wanted to calculate the external temperature of the tube. All right, so that's a hard one to get your head around if you don't know what's going on there, but you're really just doing the maths of it. Okay, so we're trying to actually look at a practical sort of engineering type problem and solving it. And you'll get some funny numbers because it is a model and a mathematical model describing a practical situation, and you wouldn't expect just nice whole numbers all the time. Okay, so study that one, and let's see if you can do some here. Here's our fluid flowing through the pipe idea here. And what we've got is a similar situation. So try to use the same ideas. And the important thing here is that we've got our constant, which we're going to sub in, and we've got the same thing as the original problem. So you'll need to use the same sort of approach there. An inner radius and an outer radius, and what we're going to do is to use the same law as before here. Okay, so it's more or less just going through the same steps, a little bit different. So go back to that example above there and use the Fourier's law and see if you can integrate it. Okay, so I'll show you the answer to that one now. Here we have two pieces of it, and part A and part B. Okay, see how you go working through that. The same idea here. There we have our integration. Okay, and sorry about that. And then evaluation. All right, let's keep going. We'll see what else we've got. Oh, sorry, I left out the other parts there for that one. Okay, let's go on and have a look at another example. Bacteria increases at a rate proportional number present. So there we are, the number of bacteria increases at a rate proportional number present. If the number increases by 10% in 1 hour, what percentage increases after a further 5 hours? That's at t equals 6. Okay, so here's the important encoding of the information. The rate of change of the number of bacteria is proportional to n. So therefore we can write this. And you should be getting familiar with this now. So separating the n, it's 1 on n dn by t equals k. It's the integral of that. Okay, so that is integral of 1 on n dn, because this is recognising the chain rule being applied. You only have to integrate with respect to n. And therefore it's ln n, and you don't have to put mod n here because the number of bacteria will be positive. Okay, you can't have a negative there. So mod n here, they've got it here, it's not necessary as n is greater than or equal to 0. Okay, so when t equals 0, you've got to make up your own initial starting value because you aren't told. Okay, so therefore it's ln of n0, n0, so therefore ln n is kt plus ln n0. So the constant here is unknown. It's a generic situation. You can start with any number of bacteria. So what's that trick? That comes from previous years of modelling exponentially. And so when t is 1, we know that it is 1.1 n0 because it's gone up by 10%. Okay, so therefore we can find k by putting in 1.1 n0, and then k is that. Looking messy, isn't it? Got to be careful here. Okay, so we can actually evaluate the K as ln 1.1. That's a trick, but this is hard here to realise how to use the 10% increase in the original and sub that in. Got to be a little bit tricky there. So we have our final equation here with no K's. Okay, this gives you an idea of how in previous years they've come about getting these sorts of exponential growths. It's interesting stuff, isn't it? If the rate of change is proportional to how much is there, you can actually create your model. And then we can sub in that t is 6 and get 1.7716. And what is that? It's increased by 77.16. You've got what you had before, 100%, plus 77.16. So these problems of an applied nature are quite challenging. Okay, so come down and see what you can do with some here. So here, question 2 through 5 there. Okay, so have a go at those and I'll show you the answer. Particularly you might look at this one. It's a motion problem and it's this proportional thing. The rate of change is proportional. So you're going to see a lot of exponentials in here because you're going to integrate one on R, one on S or whatever. So have a look at that. All right, so some of these you have to introduce your own sort of pro-numerals here. So it's a fairly difficult analytical situation. So try a few. I'll show you the answers now. Okay, so question 2. Question 3. I think we've got all of 4 there. Yep, that's 4. And question 5. All right. Now we've got a little bit more to do. I hope you're seeing a sort of method here where you need to formulate the problem, substitute in the constants that you are given, integrate it, get another constant, and then evaluate that constant. So there are certain steps that are always going to follow here. Okay, a raindrop has an acceleration of this meters per second where v is its velocity. Show that the raindrop's velocity approaches a limiting value of 29.4. Now the acceleration is the rate of change of v with respect to time. So dv by dt is this. All right, so getting v here as a single expression so we can separate it over on the other side. So this is a common denominator. So 9.8 times 3 is 29.4, take v over 3, getting all over common denominator. So then dividing both sides by that. Okay, leave the 1/3 over here. And notice that what we've done, we've actually taken out the negative in front of v and left it here over on this side. So it's a little bit simpler. You can, of course, put it across the other side as 1 over 29.4 take v, but then when you do the integration here, you'll have a negative coming out of it there. So you can please yourself there. We'll just get rid of that. You can please yourself whether you leave the negative there or take it over the other side. And so we're going to integrate this. So here's our step showing the chain rule, which means we can just integrate with respect to v, and integral of neg 1/3 here. So it's neg 1/3 t plus c. Do the integrations at the same time, so you only have to put in one constant of integration. Okay, so the ln of mod v take 29.4. Modulus has to come back because we don't know whether v take 29.4 will be a negative. Okay, so now we go into the step of looking at the given information, and obviously at time 0 before the raindrops start to fall, v is 0, so we sub that in, and we get c is ln 29.4. And so we have therefore this expression, ln v take 29.4 equals that. So we can evaluate it there and then put in the idea of bringing this across, so you're subtracting it, so therefore you're doing a division. Subtraction of logs is a division, equals neg 1/3 t. So that's a little bit of a trick there. Before rearranging this into e's to evaluate the c there. Okay, you see that trick? Rather than go down here and get it all in e's, it would be better to do it back there. Okay, so we've got then our formula, and we can rearrange this, multiplying both sides by 29.4, and then adding 29.4 at the end, or you can just discuss it here. As t turns to infinity, the right hand side, e to the neg 1/3 is 1 over e to the 1/3. So here a e to t on 3, sorry, is 1 over e to t on 3, which tends to naught for large t here. That's what we're saying. So therefore, this side is tending to naught, and v, take 29.4 tending to naught, v would be tending to 29.4 metres per second. So you really do have to stick to your guns with more difficult numbers here, and be confident that you're doing the right steps. Okay, so you'll have to concentrate on these coming problems here. Let's have a look now at some of those. So here's questions 6 and 7, and this is explicitly mentioned in the course. This Newton's cooling is proportional to the difference between temperature and that of the surrounding medium. Here it is here. How quickly the temperature changes depends upon the difference between the temperature of the body and the ambient temperature, the temperature of the surrounding medium. So the bigger that is, the faster you will lose energy and lose temperature. Okay, so pause it, have a go. Let's go down and have a look at question 8 and 9. Okay, so thinking about those, and you'll have to bring in your own symbols there using Newton's law. Okay, let's have a look at the answers. Okay, 6A and B. Question 7, A and B. And question 8 almost, I think we can get it all on there. No, not quite. There's the rest of the answer there. Question 9. Okay, last little bit now. Come down and let's see another type of problem. This is the resistance inductance circuit, explicitly mentioned in the syllabus to give you some idea of practical nature in electronics now. So here we have a differential equation. It's got di by dt, and we've got a whole lot of constants there. So the first thing to do is to change the equation by substituting in all those constants. Okay, now we can see here with separable differential equations, these two should be together. So what's a little trick here? Subtract that neg 125i from that side, and then you could factorise it and divide by the I containing term. Okay, why do we do that? Because we know that from the chain rule, this has come about. The rate of change of I with respect to t. So this is the form that we would have if we're going to want to go backwards to what produced something times the I by dt. So the I by dt is going to accompany another function. It's come about by the chain rule applied to differentiating this function and multiplying by derivative of I with respect to t. So keep that in mind so that you can see why we're separating the terms in a separable differential equation. Okay, so we've got the neg 125 over there, and so it's the integral of this, so really showing the chain rule. So we're explaining here that all we have to do is integrate with respect to I of that one, and then it's ln of mod I take 4 and neg 125t plus c, doing the two integrations in one step, both sides in other words, and then subbing initial conditions when t is 0, I is 0. That's an easy one, ln 4. And so how we've got this, remembering your log rules, subtract ln from both sides. They haven't shown it here. If I have a difference of two logs, it'll be that one divided by that log of the I take 4 divided by 4. Remember, subtraction of logs, ln A take ln B is the ln of A over B. Need to remember that. Okay, so this is neg 125t, and so we can now, notice that we've evaluated the constant back here before going to the E expression in ln. Okay, so that's an easier way of doing it there. And so now we've got the modulus of this is e to the neg 125t. Okay, so we can actually put it in at that stage there. And we've got to discuss it as t tends to infinity. So here as t tends to infinity, this will tend to 0. Okay, just check that. E to the neg 125t is 1 over e to the 125t. As t tends to infinity, this gets very big, and so 1 over it tends to 0. Okay, so therefore we would say I take 4 tends to 0 and I tends to 4 amps. So it's a fairly exhausting process to go through a whole problem like that, just making sure your maths is sound and that you can work with different looking numbers. All right, come down now and let's do the last couple of problems. I'll just go back up here. Okay, so here we have a resistance capacitance circuit, and you'll be given this there. Okay, if we want to use this, because what we're doing is applying mathematics to given models. We're not being asked right at the moment here to make up our own model. That's an exciting thing for later, where we'll be looking at finding the logistic equation, actually finding it. All right, so pause this one and have a go. Do a similar thing to what you've just seen there, and I'll show you the solution now. Okay, so there's our solution, and let's go on to the last problem and see what you think. All right, water flows out of a tap at the bottom of a large cylindrical tank at a rate, here it is, proportional to the square root of the depth of the water remaining in the tank. So this model's been done. Initially the tank is full to a depth of 9. After 15 minutes the depth is 4. So we're going to have some stuff here through which we can evaluate constants here. How long will it take for the tank to empty? So make sure all the information is on the diagram, making sure you use h there as a variable, similar to related rates questions. So what are we given? The rate of change of the volume is, that's a proportional sign, is proportional to the square root of the height, or the depth of the water. So what that means is the rate of change is k times root h. So let's now have a look at this and see what we can do. We want to know how long it would take for the tank to empty, and depth of water is 4 after 15 minutes. So what can we do here? Well, let's have a look. If we now have a look at this line here, dv by dh, dv by dt, we can change this to dv by dh, dh by dt, because at the moment we need to work in the idea of the height of the depth of the water is changing, okay, and we want to bring in the depth of the water there. So here we've got this expression, so we can then put that in place of dv by dt, Okay, so instead of dv by dt, we're going to use this one. Now, why? dh by dt is necessary because this and this, if you like, don't match. We can't integrate that, because if we divided both sides by, as we commonly do, root h, we get that. So it's a mismatch. This should be dh by dt, shouldn't it, if we're going to solve this by integration. So we've got to work a dh by dt into the problem, so we can stick it in there. So instead of dv by dt, we're going to have dv by dh and dh by dt. Now, dv by dh is going to be our next point here to actually see how we get this dv by dh. And here we're going to have to get this expression. The volume is pi r squared h. The radius here is 4, so therefore the rate of change of the volume with respect to height is 4 pi. This is a hard problem because you've got to go off and get rid of dv by dt. So we've got k root h is now 4 pi dh by dt. And we've got it. We've got a match here of that variable. This is hard stuff. Okay, so now what we need is dh by dt, the rate of change of that. And here it is, dh by dt next to this, and we can integrate it to get h. So let's put it in that form. Just come down a little bit here, and we've got now, whoops, want to go that far. So here, we're up here integrating k, and this is set up for us nicely. That's a chain rule, 4 pi, integrating root h with respect to h. Root h, or 1 on root h is h to the negative half, and now we can integrate both sides. So it's kt, and increase the power by 1 divided by the new power, so it becomes this thing. A lot of work there. And the important thing is to realise that dv by dt was dv by dr by dt, and we needed that dr by dt. Okay, so here, subbing in, we can use the fact that at the original time h is 9, so we can get c value, because t is 0, this term disappears, and so we've got c is 24 pi, and so putting that back in our equation, we've got that one, but now we need the other condition. We saw we've given two conditions up there, so 16 pi is this, and k is neg 8 pi and 15. So we've got a very complicated looking expression for root h, but we can now say when h is 0, sub it in and work out what root h would be. Here, so it'll be 0 and work out our t, our time for it to empty, 45 minutes. Comes out to be quite a nice answer once you get through all of it. So can we just recap on this up here, the idea that these didn't match. Okay, so it's an important idea here that to solve this, you had to get a dh by dt in there. Okay, so this is hard, to get this to a point where you can get rid of the dv by dt. And in fact, we need to get an expression for dv by dh as well there. All right, so study that. We must have this sort of situation here, or not that, we've got to get here an h in there, all right, to be able to integrate that. Can you see that idea? That other rate of change is needed there. All right, come down and have a go at this last problem. So, last two problems, sorry. So you might want to manipulate this a little bit so that you get, here's another one, look at this. Okay, so here, what are you going to do there? And they give you a hint. Okay, give you a hint here to set up a differential equation between h and t, being a constant. All right, so you need to do number 12, particularly as a good example of that. Okay, so pause it, have a go, and I'll show you the solutions. Down here now, question 11. Let's see if we can get it all on. Yep. Okay, have a go there. And the last question, oh, just go up a little. There we are. Number 12, I gave you some hints there. Okay. All right, getting fairly heavy there. That's the hardest part, I think. We've got some more coming up with the logistic differential equation later on, but keep going through the examples and make sure you're happy with that. But sorry about that. I'll catch you in a later presentation. Cheers for now.